Now let's resume the discussion. We're going to start with part B. All right, so we have seen the simple gear trains. We have seen the compound gear trains. And in that, we have seen the different variants of those. Now, at this particular stage, we can raise another question in order to further improve it. And you know the process that we have taken multiple times. Whenever we achieve something, we raise this question again, that is there something more we can do? And that's exactly what we're going to ask now again. What if we require further improvement in torque and in speed? Compound gear trains can do the improvements, but size is going to grow bigger. And as the size grows bigger, the number of stages grow more, and the weight is going to grow bigger as well. So that's why it is going to be a bit of concern for us that by increasing the size of compound gear train, you are going to have a bit of concerns added to it. So probably there can be alternate ways to achieve uh, these objectives, and that is exactly what we're going to try to explore. There is another alternate approach which is called planetary gear trains or epicyclic gear trains that may potentially offer a solution. Let's try to investigate that. So planetary gear trains are needed to be explained. I'll do that explanation pictorially first. Just assume that we have got a conventional gear set. This conventional gear set is quite simple to illustrate. You have gear number 2 and gear number 3 meshed together. Now what is happening is that you provide the angular velocity to gear number 2, omega n, and it produces an output angular velocity at gear number 3. And that is because the gear 2 and 3 both are grounded over here and over here. These pins can have a rotation, but the joints are structured in a sense that this is the ground link. Or you can say that actually arm number 1 is the ground link. So with this realization that you have both the ends of this arm grounded, you can readily identify that omega arm is going to be equal to 0. And that was the underlying condition of simple gear trains and compound gear trains that we have previously discussed. But in case of planetary or epicyclic gear trains, what happens is that we lift one condition. So conventional gear set is going to have 1 degree of freedom, but if you remove the ground at gear number 3, you are going to have 2 degrees of freedom. What does that mean? It means that we are going to have this ground link to be no longer implemented. So when you lift this condition, it is going to have another degree of freedom added, and this was the discussion that we had a few months earlier when we discussed the degrees of freedom. So when we do that, this is going to be the scenario. And you can obviously make this point from here by observation that this pin is no longer grounded. When you don't have this one grounded, it would mean that now you can have a movement on gear number 3 as well, around gear number 2. So with this realization that you have now got a bit different structure, we can take one step back and observe what is happening over here. So what happens is that if you provide omega n as the input, the output is going to be generated as omega out, but now you have omega arm no longer equal to 0. When you have that arrangement added, it would mean that you now need to have some modified expression exhibiting the movement. The other thing that you can observe is that the Gear number 2 is somewhat similar to a sun gear around which a planet is rotating. So that's why we call these kinds of gear sets to be planetary gear sets. You have sun to be kind of staying there, and planet is going to make rounds around it. So this is the reason why we call these to be planetary gears. But at this particular stage, you can very easily observe what was the difference. From here to here, you have shifted just like you have removed one constraint from the gear sets. And that has opened up quite a few possibilities in the movements. But the problem that we are going to face is that omega-3 that was previously readily available, just observing the gear ratios, you can compute that. But now in this case, because arm is also going to have a movement, so that's going to be a bit difficult to achieve directly omega-3. But we can do that, and that's exactly what we are going to achieve in these subsequent slides. Generally, planetary gear set is going to have another gear added to it, and that is what we call a ring gear. And that's visible here as well. Now this is going to make the whole arrangement like this, that you have the input given to the sun in terms of angular velocity, and that is going to force the arm to have a movement and the planet to have a movement as well. It depends on how you have structured the ring gear. If it is stationary, it is going to give you a different scenario, and if it is movable, then it is going to give you another different scenario. But whatever is the configuration, the planet is going to have an engagement with the ring, which is going to force the ring to have a movement, or relatively enforce the movement on the planet or on the arm. That we can take the benefit of. So this is the whole arrangement, that you have got sun, planet, and ring all structured together, assembled together to perform interesting motion. I'll momentarily stop myself discussing the mechanism part of the arrangement. I'll just invite you to consider the machine design element. Now, the one thing that you can readily observe is that you have a shaft, which center line is indicated over here. Now, this shaft is needed to be designed in a fashion that it is strong enough to hold the whole assembly together. And also, especially when the torque and force transmission is going to happen, it should be strong enough to provide that strength structurally. Also, you can see the bearing surfaces over here. These bearings are indicated. These bearings are needed to be designed in a fashion that they are consistent with the load bearing capacity or the torque capacity of the gear set. Sometimes the roller bearings are used, sometimes the thrust bearings are used, and sometimes the ball bearings are used. So it depends on what kind of application you are pursuing. The minute details, although it is not that much detailed, but the details that are available are also very interesting in a sense. Just observe what is happening on this pin. Now this pin is countersunk. Let me highlight that. That's countersunked in this part. So when you have countersinking, it means that you are going to have a special machining done in order to achieve that. And then you can see, let me use a different color to highlight that. You can see that the pin design is step design. You have one step up to this point. You have another step all the way to this point. And that is not without purpose, because over here you can see right at this particular point, it needs to have a space available. Now the pin is needed to be held together as well. So there is this lock arrangement for the pin as well. So pin is needed to have a strength to perform the job. It is needed to be countersunk so that there is no interference with the ring gear. It is needed to have a stepped profile so that the spacing is maintained. So there is quite a lot of detail in seemingly very simple, straightforward machine elements. In addition to the gears themselves, because the gears are needed to be having the gear profile generated using special purpose machines. So that's altogether a different scenario. But all I'm trying to make you see that in this particular diagram is that there is quite a lot of machine design which gets into designing such mechanisms, and you need to be aware of those. The software tools, for example, SolidWorks that you commonly use during your undergrad studies, has got the ability to perform certain analysis as well. The stress analysis is oftentimes needed depending upon the selected material and see what are the um, uh, margins of safety. Uh, and you need to be aware of those as well. So at this particular stage, uh, we we said to ourselves that we are going to try to kind of uh, hold the mechanisms discussion for a while and discuss the machine design elements. And the machine design course that you are going to study, or potentially you have already studied some part of it, is needed to be correlated over here. So there can be two possibilities for the planetary gear sets. One is what we call a fixed arm arrangement, which is being shown on the right, and the other one is called fixed ring arrangement. In the fixed arm arrangement, as is indicated over here, Sun is at the center, planets are rotating but around their own centers, and you have a ring uh, around the planets which is also rotating. So when you try to achieve this kind of arrangement, it would mean that you provide input to the Sun generally, and you provide output from the ring. And planets are going to allow you to transmit that power from the input side to the output side. And because you have multiple gears, it is going to transfer the power in much more stable and effective manner. In case of fixed ring arrangement on your left, you can see that the possibilities are going to be a bit different. And that is achieved when you say that the ground link is going to be grounded. What we have done is, like, you have this ring to be grounded, which means that once you are going to try to move the Sun, the planets are going to have a rotation about their own axis, but the arm is also going to have a movement. So this is going to be movable, which was not the case in case of fixed arm. So these are the two major configurations in which the planetary gear sets can be structured. One in which the ring is going to have a movement, and the other where you have the arm to be movable. As it happens oftentimes, there are going to be multiple different ways the epicyclic configurations can be made, and those are illustrated over here. In this particular scenario, for example, if I just take one out of those, and you can readily see that this is corresponding to configuration B. So if you observe what is happening over here is that you need to first of all realize that there are multiple gears getting engaged with each other. And the nomenclature is of specific kind. Link number one is going to be the arm always. Link number two, or designation number two, corresponds to the input side of the gear. Generally, it is going to be the Sun gear. 3, 4, up to the second last item, these are going to be the planets. The last number is going to correspond to the ring that is already described. Now, as far as the diagram is concerned, you can see that it is just like a line diagram, and it is not going to give you the complete picture. It is just like a schematic illustration, and it is only shown above the axis of rotation. And that is something like you have the axis of symmetry like this, and actually what happens is that you have the gears on the other side available. We're just like observing a truncated view, truncated schematic view of the planetary gear arrangement. So around the axis of symmetry, you are going to have, as shown in green, the ring arranged. The inner side of the ring is going to have the gear tooth profile over here or over here, which is engaged with the uh, planetary arrangement labeled as 3 to 4. The input is provided to the sun as indicated or highlighted over here, and that is mirrored on the other side as well on the about the axis of symmetry. The teeth are going to be there. Bearing surface is indicated, and obviously the sun is going to have a rotation. It is going to have external teeth profiled on the outer periphery. Ring is going to have the internal teeth. Now over here you can see one animation being run. All you need to do is to observe out of all the options ranging from A all the way to F, you need to identify this particular animation refers to what. So I'll give you a minute to observe the animation and realize uh, it refers to which epicyclic gear train. I'm hopeful that you have selected G in this case. As we did for the other mechanisms, we have to perform the kinematic analysis. In this case, we are more concerned about velocities. So the base equation that we are going to use is indicated over here. And this base equation was mentioned when we discussed the velocity kinematics many weeks ago. And in that, we said that we are going to make use of a relative velocity expression, and that was defined to be this. In our case, we're going to choose a gear. This gear is going to have the angular velocity associated with it, computed to be equal to the angular velocity of the arm added with the relative velocity. So this is the base expression. So in terms of computing it for the gear trains, obviously where you are going to have multiple gears, I'm going to list the gears over here. So starting from 2, 3, 4, and 5, and so on and so forth, I'm going to use a row by row arrangement in order to compute. So this is going to be computed when you add omega arm with the relative term over here. And once you have computed that, because you're going to start from somewhere from the input side, and input side is going to have the omega gear given, so you can make use of the terms over here in order to find out the unknown. So once you have computed that, you're going to make use of that using the gear ratios to shift to the second row, and once again through this route to the third row, and so on and so forth. Don't worry, we are going to do that exercise in the next slides. So this is going to make use of the base equation in order to construct the velocity analysis of the epicyclic gear trains. Let's do this exercise. So what we have been given is that you have a sun gear, and now if I say the sun gear, you should automatically refer to gear number 2 as illustrated over here. Sun gear is going to have 40 teeth, so that's indicated. Planet gear. Planet gear, whenever I say this word now, you should automatically refer to gear number 3 on this diagram, and this is going to have 20 teeth associated with it. The ring gear is also indicated, and now since we have already mentioned, this ring gear is going to be numbered 4. Now on top of that, like you have the number of teeth given, and even if these are not given, you can always count the number of teeth. If these gears are provided to you for a mechanism, you can always count them. But over here, these are given, these are available in the data sheet. Now, what is given like the operational arrangement is that you are rotating the arm with 200 RPM, which means that omega arm is given as well, which is the 200 RPM. Now it is also given like clockwise, and you can see that sense with the arrow indicated like this way, that it is actually clockwise. And I'm emphasizing the direction over here because this is important now. In case of epicyclic gear trains, it is absolutely necessary that you make sure that the direction is properly taken care of. So omega arm and omega sun, the angular velocity of the sun is also given as the input, which is the 100 RPM clockwise. So this omega sun is also given. So required is to compute the ring velocity omega ring. So you need to find out omega ring for the output, which is link number 4. So with this realization that you are going to use the tabular method that we have introduced in the previous slide, let's perform this exercise. Now over here you can see the simplistic schematic arrangement of the same arrangement that we have mentioned previously. So this is the same schematic. Now the rest of the stuff is indicated, like n to be 40, n2 to be 40, n3 to be 20, and n4 to be 80, and omega arm, which is going to remain constant because it is the input given to the system. And since clockwise has been taken to be a negative convention, so this is going to be minus 200 RPM. So when I use this minus 200 RPM for omega arm, this is going to be throughout constant as is indicated in this column. Now omega sun, which is going to be the angular velocity given to the input gear number 2, so that is only remain available in this row, and that's exactly what we are going to write down, minus 100. Now since in the equation you have 2 knowns and 1 unknown, you can readily compute that minus 100 is going to be equal to minus 200 plus what? 100 with a positive sign, and that's the relative angular velocity of the gear with respect to arm. And that's can be filled in this table very easily. Now since now you have all the relevant terms in row number 2 to be available, you can now jump on to gear number 3. So you cannot really do that directly. You need to make sure that you engage the gear ratio between 2 and 3 in here. And that's exactly what we have added. Since you know the 2 n2 was equal to 40 and n3 was equal to, n3 was equal to 20. So this is what we have mentioned, minus 40 by 20. And why so? Why there is this minus? Because it is going to have a change in direction. That's why it is minus. So once you do that, you can fill the rows, the values in row number 3, and that what we have done over here. So this is going to be when omega gear with respect to arm is given to be there, you can use this expression of omega gear, and this is going to give you uh, minus 200 as the answer, because this is going to be equal to minus 2. So from here to here, you multiply with minus 2 and you get minus 200. Once you have got this minus 200 added with minus 200, you can obviously find out the omega of gear 3, and that is going to be minus 400. So you can now see that when you provide minus 100 to the sun, the planet is going to rotate much faster, or rather 4 times faster. So this is minus 400 corresponding to that. So once you have minus 400 computed, you can take another jump. So you can jump from 3 to 4. And when you do that, the gear ratios is going to be this 20 by 80. And you can observe there's no sign change. Why so? Because we have already mentioned that when you have the ring and the gear is inside it like this, the direction reversal is not going to happen. So this is going to remain positive for that reason. So this is going to remain positive in that sense. So with this realization that you have minus not appearing over here, you have a positive sign, 20 by 80, like the ratio between the number of teeth of 3 and 4. So you can simply compute what is going to be omega gear to arm for gear number 4. And that is going to be minus 50. So this is just like you have 20 by 80 multiplied with minus 200. So this is going to be equal to minus 50. So this minus 50 is indicated over here, and you can now simply find out what is going to be the omega of gear number 4, which is of the ring. This is going to be minus 250, because minus 200 added with minus 50 should be equal to the answer that we have computed now. So this is your answer. And in a nutshell, it says that when you have the number of teeth to be listed like in the given data, and if you provide omega arm to be minus 200 RPM clockwise, and sun is going to have 100 RPM given to it in clockwise direction, you are going to rotate the ring in clockwise direction by 250 RPM. Let's quickly do that for another arrangement. Now this is an arrangement where you have arm over here, sun over here. This is the planet. And this planet through the bearing is connected with the ring number 5 over here. So with this data given to it, that N2 is 40, N3 is 20, N4 is 30, and N5 is 90, you can do the similar exercise. The omega arm is given to be clockwise 100 RPM, and omega sun is given to be counterclockwise with 200 RPM. So with this realization that you have got this assembly to be investigated for velocity analysis, if we plug in all these values, these are going to be the corresponding answers. So you can see that omega arm was given, so this is going to remain fixed throughout this column. When you are given omega sun to be 200, you're going to make use of this value added with as equated with addition of these two. So this is automatically going to be accounted for. Once that has been taken care of, you can make use of the gear ratios to construct this value. Once this value is given, you can readily find out the remaining expressions over here. And then using because this is the connecting shaft connecting 3 and 4 together, so this gear ratio is going to be equal to 1. So you can construct this value similarly, and similarly you can jump from this to this to find out that minus 300, which means that sun is going to have a rotation of 300 rpm in the clockwise direction. Although I'll prefer the tabular method, but alternatively you can have the formula method used as well, and that's kind of very simple. This is the formula which says that the angular velocity of the output gear minus the angular velocity of the arm divided by omega n by omega arm. Omega n is going to be provided to the sun. In terms of ratio is going to be equal to product of driver gears and product of driven gears. So when you compute that using the data given in the previous example, this is going to be your answer. Omega out is needed to be computed, omega arm is already given, omega sun is already given, omega arm is already given, and the gear ratios in terms of number of teeth is also given in these arrangements. When you plug in these values, you can automatically see that minus 300 is achieved once again, which means that the ring is going to have a rotation, is rotating in clockwise direction with 300 rpm. So I'll raise this question again. Is this it? No, this is not. Actually, we have just covered the basics, although we have all the necessary tools to understand the working of geared mechanisms and how to construct them together in simple gear trains, in compound gear trains, and in epicyclic gear trains. But you need to explore on your own quite a few other that we were unable to discuss in the class because of shortage of time. And a few candidates can be like you can observe automatic transmissions, uh, and the differential wheel assemblies can be a good interesting read. Different automatons or precision watches, you can see what are the internal mechanisms that generally are geared mechanisms. You can observe those, and that is going to give you quite an in-depth understanding of the vocabulary that we have established over here. I should also emphasize that our very own lab, human-centered robotics lab, is developing collaborative robots, or generally called cobots. And in that, we have 7 degrees of freedom robot being developed. Each degree of freedom is actually a very complex, flexible joint. And in that flexible joint, you have a motor, generally a frameless motor. You have a few sensors. You have the control circuitry of it. And on top of that, you have a harmonic drive, or generally strain wave gears added to it in order to have much more higher robust gear ratios achieved. And on top of that, quite a few other details are there. I would advocate that you, whenever you find a chance, you visit the lab and observe what are those joints and how these geared mechanisms are added into it in order to achieve backlash-free movement and a stable movement. So you can visit the lab, you can read some relevant literature as indicated in these links. So I think we can call it a day. We have covered the basics in the previous lecture, and we have covered quite all the necessary details that were required corresponding to gear trains now today. So I would once again advocate before I let you go that you need to go through the exercises, and you need to kind of develop this hands-on skill to understand all the nitty-gritty of such mechanisms. If you have any questions, you can obviously ask those in the thread in the MS Teams, or even in the comments over here in this video. So until next time, Allah Hafiz.